All right, hi everyone. Thanks for coming. So I'm pleased to introduce Nick Stone, who's visiting us here from University of Wisconsin-Madison, where he's an assistant professor. Nick Stone did his PhD at Harvard before moving to Columbia as an Einstein Fellow. He was then at the Hebrew University of Jerusalem as a senior lecturer before moving to Madison. I first got to know Nick Stone actually when he was an Einstein Fellow and I was a grad student. And I was working on an interesting observational problem, and Nick as a theorist provided something that observers love, not just a solution to a problem, but multiple solutions, which is great because you can go out and test it. And that led to a number of really cool conversations and even influenced some of the work that you might have seen Margaret Shepard present this morning at a prelim. Nick has worked on a number of very interesting aspects in dynamics, from tidal disruption events to black hole binaries, thinking about Lisa sources, as well as dynamics more generally, thinking about solutions to the three-body problem. So please welcome him here to Illinois.
Great. So yeah, thank you for the kind introduction, Decker, and for the invitation out here. It was great to come and be part of Margaret's prelim, which has also been a very exciting step on this theory observational interface that Decker referenced, because one very neat thing that we've worked on over the last year with Margaret has been showing that not just one, but all of the theoretical solutions I proposed in my 2018 paper are incorrect. And now, over the next hour, I will try to bring us to the point where we can understand why that is and why that's interesting. To give you a brief outline of what I'll be discussing today, I'm going to start with a review of tidal disruption events. And since I understand this is a center for surveys, I'm going to focus a little bit on the transition that's been underway over the last over the last decade, really, as tidal disruption events have gone from these rare one-off astrophysical transients to increasingly a statistical population of sources that in the very near future will be expanded by 1 or 2 orders of magnitude by both the Rubin Observatory and ULTRASAT's All-Sky UV survey. After discussing tidal disruption events and their observables, I will then focus on the more dynamical concept of the loss cone. For those who are not familiar with this somewhat esoteric piece of astrophysical dynamics, the loss cone is the theoretical conceptualization of how stars and other stellar mass objects get fed to hungry massive black holes in galactic nuclei. And then after wrapping up this sort of two-faced set of background material, I'll then go on to discuss the main substance of this talk, which has to do with rates of stellar tidal disruption events in real galaxies. And here I'm going to focus on 2 different observational puzzles, the first of which is a discrepancy or apparent discrepancy between sort of sky average TD rates that are predicted by dynamical loss cone theory and the sky average rate of tidal disruptions that is observed, focusing on all galaxies as a whole. And then I will zoom in on a different observational surprise, which is the apparent preference or overrepresentation that transient tidal disruption flares seem to have for a rare subset of galaxies, the so-called Post-Starburst Galaxies. So to begin, let's sort of take the broadest view possible and think a little bit about what are we talking about when we discuss tidal disruption events, or TDEs. The basic picture of a tidal disruption event was solidified in the 80s and 90s in theoretical work by Martin Rees and Chuck Evans and Chris Kachanek. The basic scenario here is that you have a supermassive black hole in the center of a galaxy and an unlucky star which has been perturbed onto a very low angular momentum, nearly radial orbit around that supermassive black hole. And once this unlucky star's pericenter falls below a few tens of Schwarzschild radii, the tidal forces from the black hole will become strong enough to rip the star apart. The spaghettified stellar debris flies off to a great distance. Half of the star is unbound and flies off to infinity, but the other half remains bound to the massive black hole and eventually returns on very high eccentricity orbits. What happens next is complicated, but a chain of events is eventually initiated, which produces a powerful electromagnetic flare. So these tidal disruption events have long been viewed as almost ideal probes of massive black hole demographics. And the reason for this is that unlike standard ways to measure the properties of massive black holes, TDs have a number of advantages. So first of all, unlike AGN, which are one of our workhorses for studying massive black holes in the universe, TDEs occur eventually in every galaxy that hosts a massive black hole, whereas AGN only occur in a small minority of galaxies, at least over human lifetimes. Unlike unresolved stellar kinematics, which is our standard tool for measuring black hole masses within the local group, TDEs can be seen to cosmological distances. So we're not just looking at a local subset of galactic nuclei, we're really looking at a very broad sampling of them. But perhaps most tantalizingly, tidal disruption events are ultimately governed by a very small number of free parameters, perhaps as few as 3 or 4. So you have the mass of the black hole, you have the mass of the star that's coming in, you have the pericenter of its near parabolic orbit, and that really might be it. If the disruption is pretty relativistic, so if the pericenter is very close to the Schwarzschild radius, then maybe you have 1 or 2 extra free parameters related to the black hole spin or the spin-orbit misalignment angle, but really you're looking at maybe half a dozen variables at most. So in principle, it seems like it should be pretty straightforward to connect the observables in a tidal disruption event, things like the time evolution of the light curve or the details of the spectroscopic features of the transient, to the underlying parameters that we care about, like black hole mass and black hole spin, the measurement of which would tell us a lot about how supermassive black holes formed at high redshift and grew over cosmic time. The devil is ultimately a bit in the details, as I'll explain in a minute or two. Aside from this one very large motivation to use TDEs as probes of the demographics of massive black holes, there are a number of other motivations as well, most of which I can't really do justice to in this talk. One of these is studying the basic physics of accretion theory. So AGN are very slowly evolving accretion disks around massive black holes, but in principle we think they're governed by a lot of the same underlying physical concepts as the rapidly evolving black hole accretion disks that are seen in X-ray binaries. The accretion disks formed in a tidal disruption event offer a relatively rare bridge between these two extrema, these two well-studied extrema of black hole accretion disk theory, because tidal disruption events form a transient, rapidly evolving accretion disk around a massive black hole, one which during a period of time of months to maybe years at most cycles through super Eddington accretion rates to sub Eddington, and then eventually down to very sub Eddington accretion rates. The super Eddington phase of accretion is particularly poorly understood at present, so TDEs offer a very nice observational window into that. In recent years, there's also been a lot of speculation that these transient accretion disks formed in tidal disruption events may be major sources of some of the high-energy astroparticle backgrounds that have been revealed by neutrino observatories like IceCube or ultra-high-energy cosmic ray observatories like Auger. So the jury is still out on this one, but it's been very hard to pin down a dominant astrophysical production site for both PeV neutrinos and EeV cosmic rays, and TDEs are a plausible contender for both of these. Going from the physics of the very small to the very big, TDEs are perhaps not interesting just for elementary particles, but also for stellar kinetic theory. So there is a lot of interesting physics related to orbital dynamics in galactic nuclei that is modeled by theorists such as myself, but still quite ill understood in a variety of ways. This physics related to the collisional dynamics of dense star systems around massive black holes is potentially very important for understanding a wide range of astrophysical phenomena, from the production of LIGO band black hole binaries to the future gravitational wave signals that will be observed by space-based interferometers such as LISA. In the Milky Way, we can actually resolve the orbits of S-stars around our own supermassive black hole, but in distant galactic nuclei, we can't really do that. And studying TDE rates gives us a rare window into what exactly is going on with dynamics in the densest stellar systems in the universe, which may ultimately be responsible for producing many of the most important gravitational wave sources we study today and will study in the future. And then finally, one very exciting motivation for me, and I think some of the people in the audience right here, is this puzzling overrepresentation of observed tidal disruption events in this tiny minority of galaxies, those that have recently gone through a major burst of star formation. These motivations, as I said, I can't really do justice to here. And while I promise that this visit is not just an excuse for me to try to sell you a book, I will note that if any of these seem interesting to you, you can purchase the first ever TDE textbook on Amazon for the price of a kidney or something like that. I'll also note that the chapters in this book are all downloadable for free on the archive. So I would encourage you to check out these individual chapters if you're curious about anything I'm discussing or not discussing today about TDEs. So I mentioned before that even though TDEs are, in principle, these very simple things to model, the devil is a bit in the details. And the reason for that is fundamentally that the aftermath of a stellar tidal disruption is a very messy three-dimensional problem in nonlinear radiation hydrodynamics. The fact that it's so messy and asymmetrical makes it pretty tough to put together a robust analytic or semi-analytic model for what's going on, and the enormous dynamic range of the problem makes it essentially impossible to simulate with either SPH techniques or standard Eulerian mesh codes. So the challenge of doing an end-to-end TD simulation is one that really perplexed theorists for more than a decade. I would say in recent years, novel numerical hydrodynamic schemes have finally allowed us to perform the first end-to-end simulations of a tidal disruption event, including what I'm going to show you right here. So in this simulation, which was run by my collaborator Elad Steinberg, we are looking at a moving mesh radiation hydrodynamics view of what happens when a star passes too close to a supermassive black hole. The arrow indicates the direction of the supermassive black hole, and the star is just past pericenter. So the tidal field from the black hole has ripped the star apart, and its spaghettified debris is now flying away to a great distance. Once the most tightly bound debris lobe reaches an apocenter that's about 100 times the tidal disruption radius, it will begin to fall back towards pericenter on orbits with eccentricities that are greater than 0.99. So in a moment, we're about to leave the non-inertial reference frame of the stellar center of mass, or the debris center of mass, and we're going to switch into a lab frame centered on the supermassive black hole as the most tightly bound debris returns. I should say that the color bar here represents debris density, so red is very dense, blue is very dilute gas. What we're seeing is, in a minute, is that a series of powerful shock waves begin thermalizing the orbital energy of the debris, and by thermalizing that energy, we reduce the eccentricity and begin to circularize this debris into something more like a standard accretion flow. The font is a little small, but if you have great eyesight, you might have noticed the clock that's been ticking away in the left-hand corner. So we've now gone from the time of disruption to about 2 months after the disruption of the star, which is roughly the peak of the light curve in a standard tidal disruption event. So this, I think, was the first simulation that ever resolved in an end-to-end way the disruption of a star up to the peak of the optical UV light curve. And by using moving mesh techniques or other relatively novel hydrodynamic approaches, I think we're now at a point where we can finally simulate these things in a relatively first principles way. Question?
I'm wondering if you can give any more details on what sets when the shocks onset, like what determines when the shocks appear.
Yeah, that is a really great and that's a great and a tough question. It's something that is currently being debated by a lot of theorists who are trying to simulate or build approximate models for these events. Roughly speaking, there are a few different shock structures or shock complexes that emerge during the debris circularization process. The classic picture of what would go on is that relativistic apsidal precession would force these debris streams to self-intersect. So the tip of the stream would precess by tens of degrees, and it would slam into a part of the stream that hadn't returned to pericenter yet. While I think this can be the dominant shock mechanism that circularizes the debris in more relativistic tidal disruption events, in a garden variety TD, where a sun-like star is disrupted by a 10 to the 6 solar mass black hole, relativistic precession is too weak for that to matter. And indeed, in this simulation, relativistic precession plays a very small role in what's going on. What we see here instead is that there's a sort of nozzle shock at pericenter. This nozzle shock is way too weak to circularize debris on its own. It's caused by the compression of the returning debris stream in the direction orthogonal to the orbital plane. But the shock does put a tiny minority of debris onto less eccentric E of 0.9 orbits. And that eccentric accretion flow winds up providing a really juicy target for the returning debris streams to slam into. So in this simulation, the dominant shock dissipation site are these stream-disk interactions. And I think that's probably what goes on in TDs like this one, but TDs span a broad range of astrophysical parameters, and other shocks may dominate for other disruptions. So great question, very open area of research. Yeah, please, in general, please interrupt with questions if you have them. Yes?
So this might be like finding a needle in a haystack, but in the Milky Way, have people ever tried to look for TDE survivors? Because I would imagine that they would look different from other stars in some way.
Yeah, also an excellent question. So within the Milky Way, we're probably never going to catch a TDE in the act. We think that the rate at which Sagittarius star disrupts stars is maybe once every 10,000 years. So we'd have to get pretty lucky. But you are right that for every star that gets tidally disrupted, there are others that sort of have a near fatal experience, but then go on to live out their lives elsewhere in the galactic center. These stars might be spun up to near breakup velocities. They also might be partially stripped and then spend a Kelvin-Helmholtz time relaxing back onto the main sequence. So indeed, people have made predictions for what these partially stripped stars would look like, or what these spun up stars would look like. As far as I know, the best candidates for these right now are some of the G clouds that are observed in the central parsec of the Milky Way galaxy. The thinking is that maybe some of these gas clouds might be the stripped envelope of a star with the intact core of the star in the center. But there's a lot of debate about whether that's what the G clouds are or whether there's something else. Yeah, thanks for the questions. Okay, so even though the theoretical picture of TD hydrodynamics is still very much unsettled, I would say that the observations have raced ahead in the last 10 to 15 years, and now theorists are playing catch up. So TDs were, even though they were first proposed theoretically in the 1970s, they were only discovered in the late 1990s with the German wide-field X-ray satellite ROSAT. So ROSAT, as well as the XMM Newton SLU survey, found the first really strong TDE candidates in the X-rays. In the modern era, the rate of X-ray selected TDE detection has been dominated by eROSITA. So these X-ray selected TDEs actually look quite a bit like sort of the simplest theoretical model you could put together for a tidal disruption event. A Shakura-Sunyaev accretion disk that extends out to this tidal disruption radius at a few tens of Schwarzschild radii. One interesting thing to note is that the emission is actually consistent with this really simple model that's too simple to describe emission from AGN or most X-ray binaries. So it's kind of like the soft state of an X-ray binary, except even often even more thermal. Currently, about 44 of these X-ray selected TDs have been discovered by eROSITA, as well as a handful more in older X-ray SLU or wide field surveys. In principle, if eROSITA ever turns back on, I think it would find many more of them, but that's a question of politics rather than science. So with eROSITA off, the current rate of TD discovery is actually dominated by wide field optical surveys. Pan-STARRS, PTF, Assassin have all done great work in the last 15 years. The current leader in the field is ZTF, but that's probably changing this year. The big surprise about optically selected TDs is that they look totally different from this naive Shakura-Sunyaev accretion disk model that seems to fit the X-ray emission pretty well. In particular, the bolometric-ish luminosity in the optical and UV bands is comparable to the observed X-ray luminosities, so maybe 10 to the 43 to 10 to the 45 ergs per second, but the black body radius is 1 to 2 orders of magnitude bigger, and the black body temperature is 1 order of magnitude smaller than what you see in X-ray, in soft X-ray emission from tidal disruption events. So it seems like something in these optically bright TDs is creating a very large photosphere on scales that are 1 or 2 orders of magnitude bigger than the tidal disruption radius. And for the last 10 years, there has been a frequently heated theoretical debate about what the geometry and even the power source of this photosphere is. And here I think maybe the deepest and most unanswered question is, what is the power source? One possibility is that this photosphere is ultimately powered by shock dissipation, and there either is no inner accretion flow yet because circularization has been too slow, or the inner accretion flow is too weak to emit a lot of ionizing continuum. The other possibility is that the photosphere is just reprocessing EUV and soft X-ray photons from some sort of inner accretion disk. In reality, probably both of these occur in different limits of TDE parameter space, but which one is dominant and over TD demographics and timescales remains very unknown at present. Currently, ZTF finds about 20 or maybe 30 optically selected TDs every year, but as I hinted at a second ago, this is changing very rapidly with the advent of the Rubin Observatory. So in this already quite dated discovery histogram in a great review paper by Suvi Ghazari, we can see an almost exponential increase in the rate of TD discovery that at the time of writing in 2021 was mostly due to ZTF. But both Rubin Observatory's LSST and the Israeli DAISY NASA UV survey satellite ULTRASAT are poised to expand our sample of TDs from about 100 to at least thousands, maybe even tens of thousands of flares. So in the very near future, we will be going from sort of small number statistics into a big data problem where one of the real bottlenecks, aside from the slow pace of theoretical developments I already mentioned, will be the challenge in getting follow-up data to confirm that the nuclear transients seen by Rubin or ULTRASAT are really bona fide TDs and not some sort of imposter like AGN variability or nuclear supernova explosions. The details of this challenge, or these challenges, are very interesting and too much for me to talk about here. So instead, I'll just offer a little propaganda about what ULTRASAT will do. Along with Yair Arakavi, I'm one of the co-chairs for ULTRASAT's TD working group. And what we're very excited about here is the fact that ULTRASAT's grasp, so the volume of the universe it's sensitive to at a given time, is pretty comparable to Rubin. The reason for that is despite having a weaker limiting magnitude, the field of view is over 200 square degrees. So ULTRASAT is really able to survey enormous fractions of the sky in its all-sky survey mode and do so with a pretty good cadence of about 3 days, which is great for tidal disruption events. We think that ULTRASAT is probably going to find somewhere between the low thousands up to 10,000 TDs per year. The main uncertainty here is the redshift evolution of the volumetric TD rate, which currently is totally unknown. We think that the ULTRASAT sample may be volume complete out to a modest redshift of 0.2 or 0.3, which will be really great for doing unbiased statistics on. And perhaps most interestingly, the synergies between ULTRASAT and LSST will be really good because in ultraviolet wavelengths, it's much, much harder to confuse a core collapse supernova with a tidal disruption event. So by having this kind of multiband information, both a near UV light curve and the LSST optical light curve, I think we can really do a good job of screening out false positives from nuclear supernova explosions. Okay, so let's let our imaginations run wild and think about this beautiful future in the second half of the 2020s, where we want to use big samples of thousands of tidal disruption events to answer some fundamental questions about massive black hole demographics. What does the bottom end of the massive black hole mass function look like? What does their spin distribution look like? What is the occupation fraction in dwarf galaxies? How are we exactly going to do all of this? Well, maybe we can think about this through the lens of what's been done in the last 10 years. So by using much smaller optically selected and sometimes X-ray selected samples of TDs, the raw thing that you get are histograms like this one, where we have the number of TDs discovered in different bins of black hole mass. But this alone doesn't necessarily tell you too much about these deeper questions about black hole origins that you care about, because after all, there are probably pretty strong survey selection effects going on here. Maybe TDs from black holes of one mass have a different luminosity function than TDs from black holes of a different mass. Maybe one TD that you saw, which happened to be from a really exciting 10 to the 4 solar mass black hole, had a really wimpy peak luminosity, and so your effective horizon for finding it was tiny compared to a garden variety TD, which could be detected out to a much greater luminosity distance. So the first step in getting astrophysics out of a sample like this is correcting for survey selection effects, most importantly, effective horizons in a flux-limited sample of tidal disruption events. So Yuhan Yao and her collaborators in ZTF have done a really amazing job doing that for about 30 TDs found by ZTF. And this black curve right here is their volume-corrected mass function of black holes of different masses. So this alone is very cool. But what if we want to do the next thing and connect this kind of mass function to deeper questions about the origins of black holes? Did massive black holes come from direct collapse of high redshift mini halos? Did they come from runaway collisions in dense star clusters? These different channels, which here are kind of sketched in cartoon form, all predict, also shown in cartoon form, different observables in the low redshift universe once you start looking at this intermediate mass black hole range. So the hierarchical nature of black hole growth in the universe, which stems itself from the hierarchical nature of galaxy assembly, means that these different scenarios kind of wash out and predict the same thing when you look at well-studied supermassive black hole mass spins. But if we really could differentiate what the black hole mass function looks like or what the occupation fraction looks like in these low mass spins, then that would be really great. But in order to do that, there's one other piece of the puzzle which is missing, which is figuring out how TDE rates themselves vary as you look at different kinds of host galaxies and you look at different kinds of black hole masses. So to go from some sort of selection-corrected mass function like this to an occupation fraction or a black hole mass function, you need to know, are the 10 to the 5 solar mass black holes disrupting stars 10 times as often as the 10 to the 7 ones, or 10 times less frequently, or maybe something in between? So this is why understanding the physics of the loss cone matters. Okay, this loss cone sounds pretty esoteric. I wasn't really sure what it was, so I asked ChatGPT. ChatGPT gave me this answer. I'm not sure I like this one, so then I decided to go into the literature. The loss cone is a concept in stellar kinetic theory which was imported from plasma kinetic theory in the 1970s by UIUC's own Stu Shapiro, as well as a handful of other theoretical astrophysicists. So the basic idea is that there is a conical locus in velocity space, which is really bad for a star to wind up in. Here, we're looking at let's say a very elliptical orbit of a star around a supermassive black hole in the center of a galaxy. This dashed circle right here indicates the tidal disruption radius. And you can see that if this is the star's instantaneous velocity vector, it's really sort of flirting with destruction. If some tiny perturbation, like a gentle breeze, perturbs this velocity vector just a little bit in this direction so that it falls into this velocity cone, then the pericenter of the star is going to move inside the tidal disruption radius, and the star will get ripped apart, making a TDE. You can also think of this process maybe not in terms of coordinate space, but in terms of the space of integrals of motion, like orbital energy and orbital angular momentum, which here is expressed in this dimensionless way as curly r. Curly r is, let's say, angular momentum squared divided by the angular momentum of a circular orbit squared. So a circular orbit has r equals 1. A radial needle-like orbit has r equals 0. In this integral space representation, the loss cone is really a loss paraboloid, and this turns out to be a slightly more convenient way to think about things because we can think about distribution functions of stars and galactic nuclei as representing a population of stars with some different density at different points in energy space and angular momentum space. So near the black hole, we expect the loss cone, or this loss paraboloid, to be empty. All the stars that used to live there were disrupted long ago, and the rate of stellar disruptions is basically the rate at which perturbations diffuse stars from populated regions of parameter space, regions with large orbital angular momentum, down to these dangerous regions inside the loss cone, where angular momentum is too small and pericenters fall inside the tidal disruption radius. As I mentioned a second ago, the theory of the astrophysical loss cone was put together in the late 1970s, building on kind of pioneering work by Bacall and Wolf to think about the diffusive evolution of dense star clusters. So when I say diffusive, the underlying physical mechanism here has to do with two-body scatterings. In most parts of the universe, stellar dynamics is effectively collisionless. So if you have some distribution of stars, it evolves in time according to the collisionless Boltzmann equation. Stars follow smooth gradients of the background potential. If the system as a whole is out of equilibrium, the system as a whole can relax, but the potential is very smooth. However, in the densest star systems in the universe, like globular clusters and the nuclear star clusters in the centers of galaxies, stellar dynamics is like a weakly collisional plasma. To leading order, stars follow these smooth trajectories set by gradients of the bulk potential, but that potential is granular enough that every now and then, stars engage in pairwise two-body scatterings with each other. Usually, these scatterings are pretty weak, and so the net result is a slow diffusion of a test star's orbit through the space of energy and angular momentum. And it was Johann Frank and Martin Rees who first realized that the main way stars get delivered to become tidal disruption events is not diffusion through energy space, but diffusion through angular momentum space. In subsequent years, in the late 1970s, there were a variety of both analytic and numerical works. Again, I want to highlight Stu Shapiro's pioneering contribution here that essentially worked out the basic theory of how the loss cone gets repopulated by diffusion coming from two-body relaxation or two-body scattering. There's some important insights and subtleties here, but I think I'm running a little behind schedule. So let's jump ahead to how on earth you would apply this abstruse kinetic formalism to some kind of quasi-realistic model of a real galaxy. Sorry, was there a hand up back there? No? Oh, OK. All right, so what I'm going to try to describe in the next few minutes is the first wave of dynamical attempts to try and make realistic predictions for how often stars get perturbed into these lost cone orbits. And here I should say this is another example of theory maybe lagging the observations a little bit, because the motivation for the papers I'm about to describe was this original set of observations by Donnelly and other X-ray astronomers who first inferred an X-ray selected TDE rate of about once every 100,000 years in a typical galaxy. So from a theoretical or a dynamical perspective, what we want to understand is, does this rate make sense? Can we explain it? Now, the sort of semi-empirical approach that I'm going to describe was first developed by Megorian and Tremaine and Wang and Merritt. More recently, it was implemented by me and Brian Metzger in sort of a 2016 update. But the basic philosophy is this. First, you assemble a sample of galaxies which are nearby enough that they have high-resolution HST photometry, which extends down to the radius of influence of the supermassive black hole. So most of the stars that get scattered into the loss cone are ultimately coming from these very small scales. They're not coming from the effective radius of the galaxy. They're coming from scales of maybe 1 to 10 parsecs near the black hole influence radius. So you really need very high-resolution photometry, and you need nearby galaxies. We use the Nuker sample for this. The next step in this simplified loss cone cookbook is to take the observed surface brightness profile, I of 2D radius big R, and then deproject it into a 3D mass density profile, rho of little r. And here in the square brackets, I'm trying to be pretty explicit about the assumptions, i.e. the weaknesses of this approach. So this step requires us to assume that the galactic nucleus is spherically symmetric. It also requires either assuming or ideally measuring a mass-to-light ratio in the nuclear stellar profile. All right, so once you have this 3D density profile, rho of r, mass per unit volume, you can then invert this with an Eddington integral to get a one-integral stellar distribution function. So this is the distribution function of stars, number of stars per unit 6D phase space volume as a function of orbital energy. Getting a one-integral distribution function, meaning one that depends on just one integral of motion energy and not two, energy and angular momentum, is equivalent to assuming isotropic stellar velocity fields. If the velocity field were very anisotropic, then this distribution function would need to have at least two independent variables, energy and angular momentum. Finally, once we have this distribution function, we can crank through the machinery developed in the 1970s to estimate diffusion coefficients. So these are essentially statistical rates of change that integrate over an ensemble of many weak, small-angle scatterings and describe how quickly a test star diffuses through the space of orbital angular momentum j. Once we have that diffusion coefficient at a given bin of orbital energy E, we can then estimate the flux of stars into the loss cone from that bin of orbital energy, and then integrate over all the bins of orbital energy to get a total tidal disruption rate. And in this step, the diffusion coefficient is ultimately dependent on the present-day mass function of stars. So here we do have to assume some sort of PDMF or maybe IMF with an extra assumption baked in. The final step along the way is, if you want to extend this kind of calculation down to very small galactic nuclei, you need to assume something about the mass function and occupation fraction of black holes in these dwarf galaxies. So in this paper with Brian Metzger from quite a while ago now, what we did was we parametrized our ignorance and assumed 5 different toy models for what this occupation fraction might look like. We have a very conservative one, this gray one, where basically there aren't any black holes below 10 to the 6 solar masses. That's almost certainly incorrect and ruled out by observations. Then we have a very liberal one, this purple one, where basically every dwarf galaxy has a massive black hole down to 10 to the 4 solar masses. What we found was that it was ultimately the runts of the litter which seemed to dominate the volumetric TDE rate. In particular, the further down you push some sort of turnover or cutoff in the black hole occupation fraction, the higher the volumetric event rate goes. So number of TDEs per cubic megaparsec per year. Here with the color-coded labels, I've shown the sort of average per galaxy rate of TDEs. So the important takeaway here, which I'll return to in a moment, after a brief intermission, is that even in this very conservative assumption about black hole occupation fractions, we find rates that are about an order of magnitude higher than what the observers are telling us. So instead of these observational rates, which are 1 or maybe a few disruptions every 100,000 years, we really had a hard time pushing our disruption rate below a few every 10,000 years. This is the first of these observational rate discrepancies, which I mentioned at the beginning of my talk, and I will return to this in a second with some updated thinking. But before I really dive into the confrontation between theory and observation for TDE rates, I do want to have a brief intermission to maybe encourage us to think a little more about whether loss cones matter beyond this narrow context of tidal disruption events. I put loss cones in the title of my talk, after all, so I have to reflect a little more broadly on this. And maybe it's obvious, but my own perspective is that I think this kind of loss cone physics, which we're calibrating right now with TDE rates, is potentially interesting for a much wider range of interesting transients and other phenomena that occur in galactic nuclei. So aside from TDEs, the same diffusive stellar two-body scatterings that bring stars into the loss cone will also bring stellar mass compact objects into the loss cone. And when that happens, we get a kind of low-frequency gravitational wave signal called an extreme mass ratio in spiral, or EMRI. These EMRIs are not seen today. They're millihertz signals, so they're below the LIGO frequency band, but they're one of the primary astrophysical targets for future space-based interferometers like LISA and Tianqin. So in the 2030s, these EMRIs are going to be particularly valuable as probably the most precise tests of GR that we're going to have. But currently, we know very little about the rate that they happen. And whether LISA will see one of these during its lifetime or 1,000 is an open question, which maybe we can chip away at today using TDE-based calibrations of extragalactic loss cones. In our own Milky Way, loss cone physics also produces hypervelocity stars via the Hills mechanism. As you heard if you went to Margaret's great prelim talk this morning, this new category of X-ray transients called quasi-periodic eruptions are not definitely, but probably related to loss cone dynamics as well. Aside from transients, there are other interesting implications of loss cones in the universe. So as I've alluded to earlier in this talk, one big question in modern astrophysics is how do massive black holes get their start? So in the high redshift universe, what is the exotic process that forms a massive black hole out of something that's not one? One of the, I would say, 3 leading scenarios is runaway collisions in dense star clusters. But the classic version of this scenario really requires very extreme conditions to operate. You need stellar densities that are above 10 to the 9 per cubic parsec, and whether or not clusters ever realize those densities is quite unclear. What we showed in a 2017 paper with Jerry Ostreicher and Andreas Cooper is that at much less extreme densities, globular clusters or empty, meaning massive black hole free nuclear star clusters, can actually generate intermediate mass black holes via loss cone-like captures onto stellar mass black hole seeds. Loss cone physics is also a key step in solving the final parsec problem and hardening supermassive black hole binaries so that they themselves can become LISA or maybe pulsar timing array sources. And in a sort of totally different context, the physics of the loss cone is thought to be responsible for the formation of the Oort cloud in our own solar system, but that's kind of a little further afield, or maybe too close to home. So, all right, coming back to TDEs and this confrontation between theory and observation. As I have said over the last few minutes, we do seem to have a bit of a puzzle here. The first decade of papers doing semi-empirical loss cone modeling basically was unable to get dynamical TDE rates below 1 disruption every 10,000 years. But what has been consistently reported by time domain optical and X-ray surveys, starting in the early 2000s with very poor statistics, but extending to the present day with pretty good statistics, is that the observed rate of TDEs is at least a factor of few and probably an order of magnitude below that lower loss cone limit. So what's going on here? One possibility is that the observers are wrong, and the main way they would probably be wrong is via an imprecise measurement of the bottom end of the TDE luminosity function. What we know empirically is that TDE flares have a pretty steep luminosity function. The relative number per bin of peak luminosity goes as peak luminosity to the minus 2.5. So what that means is that in a flux-limited survey, like what we're working with today, we're really typically seeing sort of the tip of the TDE luminosity iceberg, and most of the TDEs that are happening out there in the universe in a volumetric sense are much fainter. We're seeing a handful of them, the very closest of them, but our current time domain surveys can't see these more typical low luminosity TDEs out to a very large horizon. So people like Short Van Velzen and Yuhan Yao have done really great work to measure the TDE luminosity function. And if you read the latest ZTF papers, they think they have resolved a rollover at low luminosities, which allows them to really estimate the volumetric TDE rate. But if they're measuring that rollover incorrectly, and I think it is a little marginal, then the real rate of TDEs could be higher. That said, even though this is a possibility, my own thinking is that probably the discrepancy is motivated more, or is explained more, by problems with the semi-empirical loss cone modeling. So one explanation could be some sort of failure of the local dynamical modeling on its own terms. So maybe this HST photometry we're using is under-resolving the galactic nuclei too much, or perhaps our statistics on dwarf galaxies are too poor. They're definitely not great. Another possibility is that maybe our loss cone formalism is incomplete. So one recent idea that I worked on with Jerry Ostreicher and which was led by Odelia Tabul, a graduate student at the Hebrew University of Jerusalem, is that maybe there's additional physics missing from the classical theory of the 1970s, and the candidate we came up with was ejection and strong scatterings. And so what Odelia found is that there are circumstances in which a galactic nucleus may have a self-shielding loss cone, so that if you think about a test star undergoing a slow random walk to higher and higher eccentricities, before it gets to a fatal loss cone eccentricity, it gets ejected in a strong scattering with a stellar mass black hole. So maybe that's what's going on, although it won't happen in every galactic nucleus. But to be honest, I think while all of these are possible explanations, recent work I've done with Christian Hanna, who's a graduate student at the University of Utah, studying with Anil Seth, to be honest, I think the most likely origin of this discrepancy is just the kind of arbitrary galaxy selection criteria that theorists have been forced into when we scrounge the HST archive for any galaxy with high-resolution HST photometry. And by putting together mock galaxy catalogs that are calibrated off of the strongly biased HST selection criteria, we have sort of repeated this exercise in a series of papers over the last couple of years, and we found that this may push down TDE rates. Before I talk about that explanation, I do want to maybe just say one quick word about loss cone shielding. So this is the work by Odelia Tabul I was referencing earlier. The key piece of physics I want to mention here is that there is a sort of critical power law index for the 3D density profile, above which strong scatterings become important. So if the 3D mass density of stars falls off steeper than r to the minus 9/4, then strong scatterings become very important, and it becomes very challenging for any individual test star to ever enter the loss cone. It's much more likely that it will be ejected to infinity, or at least out of the nucleus, in one of these strong large-angle scatterings. If gamma is less than 9/4, or, well, gamma is the power law slope. So if the 3D mass distribution falls off shallower than r to the minus 9/4, then strong scatterings are pretty unimportant, and the classical theory works well. So the physics of these strong scatterings is pretty complex, but I think the conclusion is surprisingly simple. Whether or not they're important really depends on just one number, which is the power law index of the nuclear density profile. Now here I want to just flash briefly these results that Christian Hanna put together in his PhD thesis, where instead of taking sort of the HST archive on faith, we really used its results to calibrate a mock galaxy catalog. And what we found here is that in contrast to the earlier dynamical modeling I showed you from Stone and Metzger 2016, there appears to be more of a broken power law for TDE rates. So as in Stone and Metzger 2016, if we look at supermassive black holes, the TDE rate is decreasing as the black hole mass increases. But there seems to be some sort of rollover at a few times 10 to the 6 solar masses. And below a few times 10 to the 6 solar masses, the TDE rate is actually increasing with increasing black hole mass. And there are a few different ways to understand this, but I think the simplest one, which in retrospect really should have been obvious a priori, is this dashed black line right here. So the dashed black line represents the TDE rate, the maximum TDE rate that any galactic nucleus could sustain for a Hubble time. In other words, if you are a 10 to the 4 solar mass black hole and you tidally disrupt stars at a rate greater than this dashed black line for more than a Hubble time, you're not going to be a 10 to the 4 solar mass black hole for very long. You will acquire so much mass from eating stars that you will move to the right in this plot. And so even if stellar dynamics sustains this rate, you won't be an IMBH anymore. And so I think it's actually very encouraging that Christian's dynamical modeling generally seems to respect this kind of, in retrospect, obvious, but previously unexplored theoretical upper limit for what TD rates should be. Yes?
Can you explain this plot a little more? The lines, are they fits to the data, or are they fits from dynamics that are then?
Yeah, great question. Sorry I didn't explain that a little better. So each of the data points is a different galactic nucleus, which we have done loss cone modeling for in the kind of cookbook way I described earlier. Then the solid black lines are fits to those models after reweighting each galaxy by how representative it is of galaxy populations in the local universe. And it turns out that if we try to do that fit, we can't do it with a single power law. We need a broken power law. And then, so the solid black line, the broken power law, is best understood as a fit to our data, corrected as best as we can right now for the pretty arbitrary selection effects that go into the HST archive. And then this dashed black line is not coming from the data. That is a theoretical upper limit on how high a TD rate can you sustain for a Hubble time. Does that answer your question? All right, thanks for asking. I should have clarified that better. Okay, so in the final part of my talk, we're going to move on from this rate discrepancy afflicting, or perhaps not afflicting, galaxy populations as a whole, and instead focus in more detail on this really surprising observational find, which was fleshed out, I think, better than anyone by Decker French in her PhD thesis, or better than anyone at the time. I don't want to prejudice anything against her current graduate students, which has to do with this very puzzling preference that observed TDEs have for a rare category of host galaxies, post-starburst galaxies. This post-starburst preference was first noticed by Yair Arkavi in the first PTF paper, looking at the host galaxies of, I think, 3 TDE candidates. And even with a sample of n equals 3, Yair and his co-authors noticed that there seems to be this striking overrepresentation of E plus A galaxies, galaxies which recently underwent a major starburst, which in the low redshift universe make up about 0.2% of all galaxies. So you shouldn't see any of them when n equals 3. As our TDE sample size grew, Decker and then eventually other authors quantified the rate enhancement curly r that seems to be occurring in post-starburst galaxies of different categorizations. So in this classic diagram from Decker's work, here you can see spectroscopic diagnostics for star formation history in different galaxies. So on the x-axis, you have a proxy for the instantaneous star formation rate, H-alpha emission, and on the x-axis, you have a proxy for what the star formation rate was a few hundreds of megayears ago, H-delta absorption. The black dots represent an SDSS population, and the red dots represent a pretty complete sample, as of like 2016, of optically selected TDE hosts. And what you can see is that most of these TDE hosts live in a part of parameter space which is basically devoid of galaxies. So this bottom right corner are the post-starburst galaxies, which underwent a massive burst of star formation in the not too distant cosmic past, but since then have stopped making stars. The original estimates for the rate enhancement seem to indicate that in recent post-starburst galaxies, TDEs happen 50 times as often as in quote-unquote normal galaxies. In older post-starbursts, this little rectangle here, the rate enhancement was maybe an order of magnitude. These enhancements have been reanalyzed in a number of recent works, most recently by Margaret Shepard, and as you may have heard in her prelim talk. And maybe the biggest estimates for these rate enhancements have come down by a factor of a few, but it's still very statistically significant. So what's going on here? After Decker and Ann and others first quantified this post-starburst rate enhancement, it was very exciting to many dynamicists, such as myself. And in the second half of the 2010s, we wound up with perhaps more theoretical explanations than there were strong TDE candidates. So I don't really have time to get into all of these, but some of, I think, the leading explanations include binary supermassive black holes. So since many starbursts are triggered by galaxy-galaxy mergers, maybe it's natural to expect that we will have a binary supermassive black hole stirring up the stellar distribution faster than weak two-body scatterings can do it. It's also possible that the starburst that made a post-starburst galaxy was centrally concentrated so that we have an unusually dense nuclear star cluster where stars are just engaging in two-body scatterings with each other all the time. There are other possibilities as well. Margaret explained these very well in her prelim, and I'm running a little low on time, so I think I'm going to skip over the detailed explanations of a few of these dynamical mechanisms. You can ask me later if you're interested. In fact, I would definitely encourage you to, and get to how we can test these. So in 2018, in work with Eugene Vasilyev and Alexei Generozov, we suggested that maybe one way to test this wide range of theoretical explanations was to steal a tool from the supernova community, which is the delay time distribution. So these different dynamical explanations, or models, all predict different delay time distributions, meaning different rates at which the dynamical enhancement to loss cone refilling falls off as a function of time after the starburst. So on the y-axis here, we have the TD rate enhancement compared to a quote-unquote normal galaxy. And then on the x-axis, we have the time since the starburst in a post-starburst galaxy. So at the time, in collaboration with my three theoretical co-authors, we worked hard to produce theoretical delay time distributions, and we worked maybe not as hard to try and scrape together an empirical delay time distribution using the limited data that we had at the time from Decker's work. But as a theorist, it's always good to work more closely with observers. And one very exciting thing over the last year has been working with Decker and Margaret to see that the earlier empirical delay time distribution that we scraped together in 2018 was totally wrong. And in reality, it seems like TD rates are not monotonically declining with age since the starburst, but instead they seem to be growing with age since the starburst. So this is all work done by Margaret in her recently submitted paper. And I guess I would encourage you, there's a lot going on here and there's not a lot of time. So let's focus our attention on the bottom right panel. So in this bottom right panel, we have TDE rates in post-starburst hosts or rate enhancements in these hosts compared to normal galaxies. two different y-axes, but representing the same data. On the x-axis, we have the age of the burst. Here it would be 1 gigayear since the burst. Here it would be 100 megayears. And what we can see is that we don't have a monotonic decline. Instead, we seem to have an early peak in the delay time distribution, a quick drop, and a slow rise. And this slow rise is something that was very unexpected. In Margaret's paper, she really did a great job comparing her empirical delay time distribution to half a dozen different theoretical models, and really none of them matched the data very well. So I would say at this point, the DTD appears to be a very powerful tool for figuring out what is going on with the centers of post-starburst galaxies, why stars are being force-fed to supermassive black holes in these post-starburst galaxies. But at present, what the DTD is telling us is that theorists probably do need to go back to the drawing board and figure out exactly which of these mechanisms, or maybe which combination of mechanisms, can reproduce this more complicated non-monotonic structure in the observed delay time distribution. Okay, I think most of what is on this slide I just said in words. The one other thing I'll note, and here I'm just repeating something from Margaret's prelim, is that it really seems like the rate enhancement in post-starburst galaxies is dominated by the minority of galaxies that had an order unity starburst. So here we're looking at Margaret's measured rate enhancement on the y-axis versus the fraction of the galaxy's stars or stellar mass which formed in the recent starburst. And the rate enhancement is just totally concentrated in the absolute highest bin of burst mass fraction. So having a 10% burst doesn't seem to do anything. You really need an order unity starburst to pump up the TDE rate. I think this is a very important clue, but I don't know what it means. Okay, so to summarize, TDEs are a relatively rare class of EM transient. They've been predicted theoretically since the 70s. They were first observed in the 90s. So far, a lot of really heroic time domain work has gotten our sample up to maybe 100 of these flares. But with time domain surveys that are operating right now, or which will launch in 2 years, we're going to increase that sample by at least 1, and I would say probably 2 orders of magnitude. This is potentially going to be a goldmine of information for measuring the demographics of massive black holes, for getting their masses, maybe even their spins, for learning about their occupation fractions and dwarf galactic nuclei. But there are a number of challenges along the way to realizing these lofty goals. Some of these challenges are observational. Some of them are related to hydrodynamic modeling of TDEs. But one very important one is understanding differential rates. Which kind of galaxies produce which kinds of TDE rates? Here, the basic loss cone paradigm from 50 years ago is still probably our best tool for understanding how often stars get scattered into the tidal disruption radius. For about a decade, it seemed like there was a real discrepancy here between observed TDE rates and dynamically modeled loss cone rates. That seems to be going away, but maybe we haven't heard the final word on that yet. But this post-starburst preference, which no one predicted, and which really has been one of the most interesting observational surprises of our TDE sample, I would say remains totally unexplained at present, and is a very fun problem in stellar dynamics for anyone so inclined. So I'll wrap up here. Thank you all for listening, and I'm happy to take any extra questions you have.
Could you say something about the potential observational bias of, I'm just imagining like starburst galaxies being optically thick at the center and so you don't see it?
Yeah, that's an excellent question. There have been a number of papers, or maybe a number is too strong, but there have been a few papers in recent years trying to understand whether this post-starburst preference could just be a selection effect related to preferential like dust absorption or neutral hydrogen extinction in regular galaxies. And Margaret has done some work on this. There's also a very nice paper by Nathan Roth from 2021, I think. And the general conclusion is that this may alleviate the post-starburst preference, but it seems like it doesn't eliminate it entirely. So it is challenging to explain it away as a selection effect created just by too much dust obscuration in the centers of normal galaxies. Yeah, thanks for the question.
So the supermassive black hole binaries, I could imagine at later times it might deplete the lost cone, right? So
Definitely.
is it like it's an enhancement early on and then a suppression later or something like that? Or
Yeah, your intuition is 100% correct. I had to skip over this slide because I had digressed a little too much, but that's basically what's going on. So when you have a supermassive black hole binary, the rate of TDs can be enhanced by many orders of magnitude by a combination of two effects. One is strong scatterings off of the massive object. The other is the Kozai-Lidov effect. So this is a secular dynamical effect, which was first discovered in the context of the solar system and moons of Uranus. So these two effects together can increase the TD rate from 1 every 10,000 years to maybe 1 every year at peak in extreme cases. But this enhancement is very short-lived because you chew through all of the stars, and then the in-spiral sort of stalls out. So here you can see some nice theoretical modeling from Chris Wegg and Nate Bode of the TDE rate in one of these binary black hole nuclei as a function of time in megayears. So you get this huge enhancement, but it only lasts for a few megayears, and then it goes away, and eventually you go back to a lower rate than what you had before. You can extend the duration of this enhancement a bit by having a pretty eccentric binary black hole orbit. Then the nature of the Kozai-Lidov effect changes, but even so, it is kind of a burst and then a suppression. Yeah, good question. Yeah, thanks for coming.